Boa tarde, bem-vindos ao seminário de computação gráfica do IMPA. Hoje temos o prazer de receber o Arthur novamente, Arthur Bizz. Arthur está na EPFL, trabalhando com Neural Kolmogorov Equations. Arthur estava na EPFL, agora está na Imperial.
Porque, pessoal, vocês vão desculpar, eu vou falar em inglês, que tem um pessoal aí fora assistindo. Okay, so, hi everyone. I'm Arthur. This is part of my work at EPFL with Professor Olga Fink. And hopefully we'll be able to discuss a little bit about this new architecture we're trying to come up with called Neural Kolmogorov Equations and how they communicate with SDEs, generated learning, all of this stuff. So I was currently at EPFL when I did this, along with Olga. Very soon I'll be in Imperial College, as Thiago said. This is my email. Otherwise, you can reach me through any other means. That should be fine. And so basically, the basic structure for the presentation. So we'll talk a little bit about what NeuroODs and SDEs even are, for those of you that are not aware. We'll talk a little bit about this new architecture that we're proposing, and finally show some results and possible future steps. Okay, so NeuroODs and NeuroSDEs. So basically, try and keep it short. There's this entire burgeoning field of scientific machine learning, right? And most of it has to do with this fundamental limitation of analytical methods, right? Because real systems in industry, for example, as we were very much interested in, but also in finance, are related. They are too big and too complicated for you to try and express them in terms of analytical equations, right? So another way for us to do this is, instead of trying to derive these models in closed form, we instead learn these dynamics from data, right? So what we can do, for example, and this is the object that we'll be most interested in throughout the talk, are NeuroODs, right? NeuroODs consist essentially in, you have some dynamics, either physical or in finance or whatever it is, that evolve in continuous time. You want to describe them as a differential equation, and you're going to train these differential equations, you're going to learn them with some neural network that you will extract directly from data. So at least in principle, you shouldn't have to know anything about the system, just have enough observations from it to be able to tell how it works and hopefully be able to make predictions about how it will work in the future, right? So NeuroODs, what they do is they look at, say, a time series for a system. Let's say you have Dolores attractor. You have many samples of what it does across time. What you can do is, well, you're trying to model this vector field that will generate these samples that you've seen, right? So, cool, the GIFs are working. So basically what we have, let's say, for example, look at the plot on the left. What we have these time series, these plots essentially. And as you can see, the neural network, just by looking at the variation in this data, it is able to learn the derivative. And by learning the derivative, you can learn basically the dynamics in terms of this differential equation, right? So the fundamental part about this is that, well, when you're doing inference for these models, you're essentially integrating an entire differential equation whose vector field is given by this neural network. So at each step of your integrating scheme, you're having to go through your neural network again and again, so that is extremely expensive. So generating new data using these means is kind of expensive, but for ODEs, training them is very simple, right? You have your data, you can calculate slopes, maybe using some finite differences or something like this. And the advantage is basically you can just train on all of your data points simultaneously. This is very easy to do because, again, your data is very smooth, everything is differentiable. So while you want to learn the derivative, you just differentiate your data and learn that directly, right? Unfortunately, the systems that we were interested in were not deterministic, right? And this introduces a whole lot of problems. So in industry, in finance, for these generative models, all of this stuff, systems are not stochastic, are not deterministic, right? So this means that they're random by nature, and specifically, if you know a current state, you cannot really know what it's going to do in the future, right? This doesn't seem like such a big problem at first, but the big issue now is that essentially we have randomness will fundamentally break the way that we train these models, and we're going to have to come up with something almost entirely new, right? And there are two kinds of randomness. The one that we're most used to is basically what we commonly would call just noise, right? Is this kind of continuous, relatively small scale randomness, which is most naturally modeled by a Brownian motion, right? So these are small oscillations around things that relate to Gaussian noise, Gaussian spreading, all of that stuff, right? But in industry and in finance, which were two of the applications we were interested in, there's a second kind of stochasticity, which is much more aggressive, right? Which are these Lévy jumps, right? So these are not continuous. They are, in fact, just random explosions, random shocks that will break your system. Say, for example, you're in industry and, well, the market crashes, basically, or you have some machine that jams or breaks or whatever. So we can't really model these sudden catastrophic events with just continuous, tame Brownian motion. So we need something else, which are these Lévy jumps, right? And basically, what we're going to have to go beyond ordinary differential equations, right? The first step beyond differential equations would be these regular SDEs. So as you can see, we still have our vector field F, which is our deterministic dynamics. But we also have now this noise term G, which is multiplying our white noise. So do note also that the amount of noise that we have in our system is not pure. It may depend on our state, for example, and this will introduce all kinds of complications afterwards. And this is usually the kind of thing that regular systems, the existing stochastic differential equations would deal with. But unfortunately, fortunately, because it's quite interesting, but it makes it much harder, we also need to include these catastrophic discontinuous jumps, right? So these random, strong perturbations, which are associated usually with what people call a Poisson jump process. I'm just going to give a caveat now. I am not a probability guy, as you guys will see. I will very quickly try to run away from it into PDE theory. So do not take my word on this. Afterwards, I can share any sources or whatever. If I say something wrong, please let me know. But as far as I can tell, right, we could imagine, for example, are there any other kinds of randomness that we're forgetting about, right? And what is interesting is that there's this Lévy-Kinching theorem that actually tells you no. To some extent, right, if your system is Markov continuous time and obeys certain technical assumptions, this is the most general possible random Markov system in continuous time, right? So what we're learning here is, at least in principle, extremely general, but again, this comes with challenges, right? And training these guys is extremely hard because, again, the naive way to do it, which is to just differentiate your data, see those slopes, and make your neural network learn that, no longer works, right? First, because noise is not differentiable, so it doesn't even make a lot of sense to try and differentiate your time series to begin with. But even worse is that you don't have uniqueness, right? So for a single point, you can have, for example, as we can see, this is one of the data sets that we were using to calculate the degradation of batteries. Of course, each one of these batteries will be going through a completely different degradation cycle. So given an initial point, you don't really have one point that will follow, but probably many, covering a probability distribution, right? So even if you could differentiate, even if you could calculate derivatives here, it's unclear which one of these slopes you should choose, right? You could, for example, maybe try to just model the average behavior, but this wouldn't allow you to do uncertainty quantification, right? So we're not only interested in determining what happens on average, we also need to know what are the possible extreme events. For example, for these batteries, as you can see, there are some lines of tendency, but around these lines, things spread out very, very drastically. So, and finally, no models, or to be correct, very few models nowadays can handle jumps. So these catastrophic, discontinuous kinds of randomness. And we're going to have to try somehow to tackle all of these problems simultaneously, right? First, let me go over the literature very quick, just so we know what we're comparing against. There are basically two kinds of neurostochastic differential equations. Either there are SDE guns and models similar to these that basically, because you cannot differentiate noise, what they end up having to do is they generate, say, millions of stochastic trajectories and repeatedly. And each time after they generate all of these trajectories, they compare the distribution of these trajectories with the data using a system that's similar to guns. Hopefully, most of you here will know generative adversarial networks, right? But these are very expensive. Guns are famously ill-behaved, hard to train, right? So they are very bulky, but they do work, right? And this is what was being done until, say, 3 years ago, I think. But some other methods, inspired also, say, by diffusion models, flow matching, all of that stuff, have started doing something slightly different, which I am going to call as an umbrella term, using these Euler-Maruyama discretizations, right? What these other models do is, well, they look at your particles, they look at the trajectories, which are stochastic or whatever, and they say, well, I'm going to pretend that I can differentiate noise anyway, which is kind of dangerous, but machine learning, we often do some rather wild assumptions. And basically what they try to do is, hopefully, the illustrations will be very, very rough, by the way. But what they do is, well, say we have these three particles in some given moment in the past, and after some time of random motion, they show up again in the future in some new position. I'm just going to pretend that between these two observations, they followed essentially a straight line. And well, I'm just going to tell my neural network to try and learn that as best as possible. The things that it cannot learn directly by interpolating between points, we would just say that's noise, right? If you think about it, this doesn't really, statistically speaking, if you had infinitely many samples, this will end up working. If you had infinitely many samples and your observations of your time series were very close together, this could make a little bit of sense. If you go outside of this regime, things start getting much more complicated, right? Can you really just say that a random particle has followed a straight line between your two observations, right? And what does it even mean, for example, so you make, looking, for example, at the particle on the right, this one that I separated, so you find this one estimate for where your particle should have gone according to your deterministic model, and you say, well, whatever my deterministic model cannot explain, I'll just say that's noise. That's the way that they do it, and to some extent it does work, but still, we're going to try to do a little bit better than that. So basically, current neuro SDE models, so current models for stochastic dynamics in continuous time, they're lacking in two ways: scalability and noise diversity, right? So autoregressive models like GANs, they're very bulky. They do not scale because they need to generate all of these trajectories in order to be trained. All these other models, Euler-Maruyama, these finite difference models, they are scalable, but they're not very accurate because they depend on these rough assumptions. And both can only learn very simple forms of noise, right? So basically with very few exceptions, both kinds of models either need to assume that your noise is uncoupled, diagonal, very well-behaved Brownian motion, and that it has no jumps at all, right? Which is not realistic for most of the applications that we were talking about. So we're going to have to, and well, we want it all. We want to have a model that is fast, that can be trained very quickly, but also has all kinds of flexibility so that we can model all kinds, preferentially, as I said, if we can cover all kinds of possible continuous time stochastic systems, that would be fantastic, right? And this is where we're going with the Kolmogorov equation, essentially. So the Kolmogorov equation, this is a shift in perspective. As I said, I am not a probability guy, I'm much more of a PDE guy. Unfortunately, there is this bridge between the two. And the Kolmogorov equation, also known as the Fokker-Planck equation, we would have called it Neural Fokker-Planck equations, but someone has published a paper with that name already. So we had to go dig through the literature to see if we could find an alternative name. That's what we went with. So the Kolmogorov equation, it means a shift in perspective, right? Instead of looking at each particle individually, we want to know now, well, okay, on average, or even better, statistically speaking, what are these particles going to do, right? So if we have infinitely many particles, we can imagine, like in the image on the right, obviously we're always going to have finitely many observations, but if you look at it very far apart, we can imagine that these clusters of particles are actually smooth, continuous objects on which we can do calculus, right? And so what the Kolmogorov forward equation tells us is basically how to translate a problem about random motion of small particles into macroscopic motion of these probability densities, right? So we're going to now model how all of these particles move at the same time, and it's given by this basically by three terms, right? Like in our SDE, we had drift, noise, and jumps. Each one of these will show up as a different differential operator in our PDE, which I called LA, LD, and LJ, not very creatively. And what we'll have basically is that again, each one of these guys will be doing something different to our probability distribution, right? So one way to think about what is, for example, on the image on the left, does this work? Unfortunately, people online cannot see it. Well, what you can imagine is that underneath this Gaussian that is spreading, we can imagine that we actually had lots of particles that at some point were concentrated a little bit around the mean of this Gaussian, but very slowly they start spreading out and moving a little bit towards the left. Right? And this is, again, this kind of average microscopic vision of what these millions or billions of particles would be doing in some sense, right? And essentially, so we have these differential operators, and the evolution is given by the semigroup, which unfortunately didn't compile in LaTeX, but this is the exponential of these operators, basically, right? So these guys, LA, LD, and LJ, give us the infinitesimal variation in how these things work. And their exponential then, given basic spectral theory, will tell us how they actually propagate the probabilities forward in the future, right? However, PDEs are infinite dimensional, right? We cannot really model a PDE. I mean, this is elegant in principle, right? We can do this, but how could we predict and model the behavior of a system that is quite literally infinite dimensional, right? That doesn't make a lot of sense. So what we learn in most of numerical analysis, for example, is that PDEs must always be discretized. They must always be projected onto some kind of finite dimensional space before we can actually do anything with them, before we can do computations, right? There are many, many, many ways to discretize a PDE and to transform it into a finite dimensional object. What we will do is we will use Galerkin methods, right? Galerkin methods are basically, you're going to see how your dynamics work on a subset of basis functions. And hopefully by seeing how each one of these basis functions evolve in time, you can combine them, and hopefully now you can model at least a very wide family of distributions so that we can see how this is going. Many of you here will be by now very familiar with this approach. We have published a couple papers on this kind of stuff for the wave equation, for example. But for each problem, we need to find a different representation, right? We could, for example, try to use, Fourier series to represent the solution to these PDEs. But the problem with Fourier series is that they blow up exponentially fast, right? So if we want to do a stochastic system of order 4, that's already unfeasible because we would need 100 to the 4th power Fourier modes. And the systems that we were working with were often dimension 10, 14, 20. So that would be completely unfeasible. What we did instead, inspired by this family of numerical methods called smooth particle hydrodynamics, is that we're going to choose another basis family for our function space in some sense, which are Gaussian mixtures. So what we're going to say, and this is a relatively strong assumption, but still, we're going to assume that the probability density for our particles can be well given by a sum of Gaussians, right? These normal distributions, which are fancy n. Each one of them will have a weight pi, a mean mu, and a covariance sigma. Hopefully everyone is familiarized with how these Gaussians look like in space. I will have a few more illustrations afterwards. And basically what we will imagine is that now instead of having single particles moving randomly around space, we will have all of these Gaussian masses, these macroscopic densities that are traveling through space that will give us more or less a probability distribution for where each one of our particles is, right? There are some technicalities on how to do this. I won't go into detail in order not to bore the audience, but these projections from infinite dimensional space onto these spaces of Gaussians and then going back, they can get pretty ugly quite fast. In particular because unlike Fourier series, for example, a representation of a function using Gaussian mixtures is not unique. There are all kinds of crazy, very dirty things that we have to do in the appendices of the paper that hopefully no one will read. But in the end, we're able to define the dynamics of the system on this very reduced dimensional space. So we went from infinitely many dimensions to basically we just need to see how each one of these Gaussians move and spread across space. And to be very explicit, what happens, so we want to model the dynamics of our macroscopic system in terms of sums of Gaussians. And we know more or less what the Kolmogorov Fokker-Planck equation does to Gaussians. And essentially, the advection component, which is the deterministic transport, it will move your Gaussian, essentially. The diffusion component, which will be given by your random, small, continuous grounding motion, will make your Gaussian spread out. And finally, jumps will make your Gaussian split, right? So we can imagine, for example, that if all of our particles are concentrated along a single point, but your jump can either go left or right, we will split our one Gaussian into two smaller Gaussians, each one for one of the jump possibilities, basically. And now that we have modeled, well, all three of these operators and how they act on our basis, we're done, right? Again, there's all kinds of crazy technicalities that we have to go over, but at least in principle, we know how to do, right? So we know how each one of the components in our deterministic and random dynamics reflect on our family of basis functions. So now we can model each one of them individually, right? And for an example of how this would look like in practice, what we have here, so imagine this is an SDE in phase space, right? This is a stochastic harmonic oscillator, as simple as it gets, right? So we have the deterministic trajectory is the little black dashed line that goes in a circle, right? And if our particles were evolving in a purely deterministic fashion, we would see that they would just be on top of this line, right? However, we have, again, our particles are doing all kinds of random crazy motion. So this is why they start at, let's say, midday, and they go around one full cycle. So if you pay attention, you'll see that the distribution, the particles, the trajectories start all very close to one another. But as time goes by, because of randomness, they start spreading out, right? And they start going further and further away. But again, it's hard to tell what is happening from an individual particle perspective. What we can do is we can try and fit Gaussian distributions to each moment in time of these particles, which is given by these. We can imagine that we're looking at this picture from above, right? And these little circles are the Gaussian distributions for the position of our particles, and this manifests on the thing on the right, right? So what we have essentially is that now we have a family of these, each one of these is a snapshot in time, and what we have is that our Gaussian is going around in a circle and spreading out. And this model is exactly, and this is in fact much more informative than just looking at the particles individually, because now we have this broad view of the dynamics, right? Our Gaussians are going around, they're spreading out. This tells us more or less exactly what we want to do. And again, we can do this in a purely deterministic way. That will be the key thing behind our neural architecture. This is why we're calling it Neural Kolmogorov Equations, essentially. And the idea with Neural Kolmogorov Equations, the idea with Kolmogorov equations is exactly that. Of course, in nature, we only observe each one of these particles or each one of these stocks or whatever other object, microscopic object will be behaving stochastically, but we can approximately fit Gaussian distributions to large amounts of these particles, right? And then we can just see how each one of these Gaussians evolve with time, essentially, right? Again, there is all kinds of approximation theory that we need to use here in order to make this precise, but in a non-rigorous manner, we know that the action of this generator on our Gaussians has three effects, which is to carry it through advection, spread it through diffusion, and split it through jumps. So we can model each one of these guys with a neural network, basically. And again, the advantage is that these things are deterministic, right? So now we're back onto deterministic things. So like we could in NeuroDEs, we could just differentiate data. Now we can, again, just differentiate things because everything should behave, at least approximately, smoothly. We have derivatives back. So we can do all of these things in parallel. No longer will we have to train or simulate thousands and thousands of stochastic trajectories to learn anything. We can just look at how these particles move. And even though each one of them moves in a way that is not differentiable, their clusters, their macroscopic behavior will be smooth, will be deterministic, and will be differentiable. So we can now just differentiate it and calculate it, and that will be it. So basically, this is the big picture. I had a more technical slide here that I hid. If anyone has questions, we can go over it later. But one of the cool things that this allows us to do is that, we're calculating, again, the semi-group, this evolution operator over these Gaussians, right? So we have these generators, which are the infinitesimal change, and we have what actually propagates these guys forward is they're exponential, right? We have, from numerical analysis theory, and I won't go over this very much, we have different ways to split up the exponential of a complicated operator And one of the cool things that we do in the paper is that we prove that these Euler schemes that we were talking about, which are just imagining that your trajectory follows a straight path between one observation and the other, these are equivalent to what we call Lee-Trotter operator splitting, right? So in other words, what you have is that the exponential of the sum of the advection, the diffusion, and jump operators, you can just approximate it very roughly as first you advect, first you move, then you spread, then you jump. This is exactly what these other models do. But because now we have access to all of this theory and we can put it in the context of differential equations and so on, we can use a little bit more interesting and more powerful ways to break up these semi-groups, to break up these evolution operators, basically. For example, using strength splitting, right? Which is a bit of a fancier way to approximate these exponentials of composite operators that, in particular, they give us much more accurate behavior, as we'll see very soon, right? And the intuition that we can do is, well, because we're looking at these macroscopic distributions, we can no longer just look at how they're propagating towards the future, but now because everything is deterministic, we can also look how they propagate towards the past. With things are stochastic, you can't really do this because you can't really go back in time with stochastic processes, but when things are deterministic, you can. And now, because we know how things evolve forward in time as well as backward, we have more information to approximate these derivatives of these objects, how they evolve with time, and so on. So basically, we can calculate more accurate, more powerful dynamics from our observations by looking at how these particles move forward and backward in time. Technical slide for the purposes of intellectual intimidation. If anyone's interested afterwards, I'll send you the link for the archive, right? So when you take all of these intuitive arguments, like, okay, we have this function space, we calculate how these generators act on this function space. This is what we end up with. And very roughly, what we can think is that, well, the advection operator, the deterministic transport operator, takes our mean using our drift F, and also changes the spread, the covariance of our Gaussian using something that is also correlated with F in a very complicated way that I won't go over. And likewise, the action of the generator, of the diffusion generator over our Gaussians does not change anything about the mean, so it doesn't move specifically our distributions, but it does make them spread. Trust me, this is what this slide is saying to some degree. Again, I won't go over it, not to bore you to death, but we can turn these first two lines of calculations, which are very abstract and kind of complicated, into very concrete loss functions that we can train over, basically, right? So because we know that these generators work like this, well, our neural approximation for these generators must work more or less in the same way. They must transport, spread these distributions exactly in the same way. This leads to these ugly, but trust me, they work, and you'll see soon, expressions for how we calculate these loss functions for these networks. And in practice, if we forget about the equations a little bit, what we have, this is the big difference between what we're doing and what people were doing before. So as I said, these Euler-Maruyama methods that are very quick but are inaccurate, they just assume that your particle moves in a straight line, and well, whenever that model doesn't work, they say, it didn't work because of noise, and that's how they model both deterministic forces and noise. We're doing something a little bit more elaborate. First of all, we take all of these particles and we kind of place them inside these clusters, which will be our approximations for these Gaussians, for these blobs, right? Which are represented by these circles. And then, well, we have that our particles on the left were particles at time 0, particles on the right were particles at time 1. We can see how our Gaussians would move forward a little bit and see how our Gaussians would move backwards a little bit. And these two things should match, right? This is what we're trying to say in the figure, in the first half of the figure on the right, okay? And so we can make the centers, the means of these Gaussian clusters match. And so essentially what we have is that the means of these guys, even though I wrote them as straight lines, they no longer need to move exactly in straight lines. So we're having a higher order approximation for how these clusters move. But also once we have how the clusters move, we can also see, well, how they're spreading. And however much spreading cannot be attributed to our deterministic dynamics must come from the noise, right? I've said a lot, but this is, if you're going to take home anything, this is the idea. By clustering these guys into macroscopic objects, we can see how these macroscopic objects evolve with time. We can compare their means of these Gaussians, as well as the covariances or the spread of these Gaussians. And each one of these things will tell us something different. It will tell us about deterministic transport, about diffusion, and afterwards about jumps. This is, I think, the most unfortunate illustration of the paper, but it does make sense in context. And what we're trying to say is that also, for example, when we're learning jumps, the idea is the same. To learn these jumps, what we have is, if we model our jumps also as Gaussians, we're still on our manifold. So we can model the effect of this splitting effect as a convolution of Gaussian mixtures with other Gaussian mixtures, for example. And again, in very technical terms, we can basically separate each one of these effects differently based on how they act on these Gaussians. And then we can just compose them using these properties of the closure of Gaussians under convolution, right? In particular, this only works because a Gaussian convolved with another Gaussian is a Gaussian mixture convolved with another Gaussian mixture is a Gaussian mixture. So if we can say that our current distribution is a Gaussian mixture, and the jumps that it will take can be modeled as a Gaussian mixture, what we will have is that the splitting that is induced by the jumps will just become some kind of convolution operator on this submanifold, right? And this is more or less what I was trying to illustrate. My co-authors have informed me that this is not very clear from the image, and I apologize. I am taking suggestions for how to illustrate this better, okay? But this is the basic idea, and well, am I going too fast? No? It's kind of it. So just for some results very quickly. So on the left, so this is the Lorentz oscillator, right? So this is a famously hard to model kind of chaotic three-dimensional system, right? And we're making it even worse by adding geometric noise to it, right? So basically what we do is we have already this stochastic system, and then we add randomness to it to some degree. So as you can see, the trajectories are kind of rough. I mean, it's hard to see because I think these are 1,000 trajectories overlaid. But if you look at each one of them separately, they look kind of weird. And you have this kind of spaced out, but still somewhat concentrated dynamics, right? Then if we use these Euler-Maruyama, which are these first order kind of rough approximations to the dynamics, we get the model in the middle, right? And as you can see, that is much more spread out. What's happening here is that basically these lower order models, they try to approximate these deterministic dynamics in a way that is not very good. And if you remember, the basic principle was anything for Euler-Maruyama, for these first order methods, anything that they cannot model with deterministic terms, they will model as noise. What ends up happening is because their deterministic model is very bad, they need to attribute lots of things to noise. So their end result is that their model is much more noisy than the actual object that we're seeing, which leads to this much greater spread, right? As you can see, the Lorentz attractor is very much deformed, even though you can tell that like generally speaking, qualitatively, it kind of nailed the behavior. You can see that it has overestimated the amount of noise that we have in the system very much because, again, their modeling was not very good. Meanwhile, our system looks almost entirely identical to the one that we began with because we're no longer looking at each of these particles individually. We're looking at these big macroscopic masses moving around this attractor. This gives us a much more accurate approximation for how the deterministic part works. And then once we know how the deterministic part works very well, we just look at the noise as a small adjustment, as a small perturbation around what we were doing. So as you can see, we get a big jump in accuracy here. And also, strength? It's strength splitting, yes. We're using strength splitting for this, which is a big difference, basically, right? But we can only use strength splitting because we're in this macroscopic level. If we were trying to use string-like differences on the SD trajectories, that wouldn't work for technical reasons. So we kind of have to combine the two in some sense. Lead rotor in the middle.
Would be the same as
No. So it's Euler-Maruyama in the middle, strength splitting for Kolmogorov, right? How do I, the numbers? So basically what we did was we used the Wasserstein distance over all moments in time across many dimensions. Wasserstein distance is that metric between probability distributions, basically, right? And we also evaluate whether the mean and the covariance of the distribution at each point kind of matches or not. So measuring the distance between two probability distributions has been perhaps the most non-intuitive part of this work for me, because again, I know nothing about probability, but the numbers also show up, and hopefully, I don't remember if I included the table, but it might show up at some point, and the numbers are also pretty nice, right? And this image is not as, it looked more impressive in the small screen. Well, this is a similar principle. So now we have a somewhat more complicated stochastic process. We have the double well system, right? So you can imagine this as you have perhaps this gradient that has two equilibrium points, and our particles would be stuck in either one or the other potential well, but they have jumps. They have these shock-like behavior that sometimes are strong enough to make them switch attraction basins, as well as they also have continuous randomness sprinkled throughout. And what is clearer in the small screen is that, again, the Euler-Maruyama model kind of overestimates the noise quite a lot and doesn't get the noise quite well, while our system, it can reproduce the qualitative behavior of things much better. Again, the numbers are more impressive, but hopefully the idea is clear that when your deterministic model is not very good, you attribute your error to noise, and that makes your representations more noisy also. Some limitations, basically. When we started out, we were hoping that we could use this also for generative AI, say flow matching, diffusion models to generate images, all of that stuff. Unfortunately, this is probably not the case, at least not as we imagined it, because basically we need to be able, this is a basic assumption, right? We need to be able to model things with Gaussian mixtures. And Gaussian mixtures work very well up to dimensions, say 20, 30, perhaps. Diffusion models work in dimensions in the hundreds, right? So now in these very, very high dimensions, you would need a huge amount of particles to model a single Gaussian. Basically, Gaussians in these super high dimensional spaces become kind of meaningless. So we wouldn't really know, at least for now, if anyone has suggestions, how to extrapolate these things to higher dimensions, right? And basically, but still, for relatively small numbers of dimensions, or at least for a very, very large number of samples, we can state that basically Neural Kolmogorov equations are in some sense optimal, because they do converge to these real generators, right? So if you have infinitely many particles, you can know exactly what the deterministic, continuous randomness, and crazy randomness factors each one is, basically. And the road ahead, well, yeah. Yeah, so what we are doing basically is we use about as many Gaussians as there are particles in the system. So this can get quite expensive, right? So for diffusion models, we would need, say, millions of Gaussians, about one for each image, and that would just be kind of crazy, right? But, again, the applications for now are kind of different, but there might be ways to make it scale better, right? Yes.
So using these basic rules of evolution by each of the generators, right?
Exactly. So we can parallelize over the Gaussians, right? Because the equation is linear, we don't really need to know what is happening to other Gaussians to determine what this one is doing. So again, everything is parallel, fortunately, which makes it scalable and fast. But again, we need Gaussians, and this is not viable in super high dimensions.
Is the flow also deforming the Gaussian?
Yes, the flow. So if the first line, second inner product is the deformation of the Gaussian by the deterministic flow, right? Yeah. And just to finish, so we can move on to more questions. So basically, we did lots of experiments on scientific machine learning benchmarks, but still relatively synthetic, I would say. Our idea would be to go over to do some very large-scale experiments, like in molecular dynamics or coarse graining for fluid systems, that kind of stuff. And yeah, hopefully at some point we will be able to do something akin to generative models, at least for physical systems, that kind of stuff. And yeah, this took us some time, but now we're very, very happy about it, and hopefully we'll be able to do some cool stuff with it. So having said all that, yeah, so take-home picture, you lift this stochastic, ugly system onto an infinite dimensional deterministic system. Now you discretize this guy onto, again, finite dimensions, but now projecting onto this manifold of Gaussian mixtures by choosing these basis functions. You split each one of the operators because each one of them does something very specific to your Gaussian. You learn each one of them basically like you would with a regular Neural ODE, because everything is deterministic now. We can take derivatives in time. And finally, we learn jumps also by modeling them. Everything is Gaussian in our beautiful world of assumptions here. And essentially, so far, they have shown good accuracy, great speed, and yeah, that's it. So thank you very much. So if anyone has any questions, I would be happy to take them. I will. Thiago, would you get the questions? Well, you're paying attention, man.
Yeah. So you approximated the jump part with the Gaussians.
Yes.
And so are you essentially trying to approximate like one process using Gaussians?
Essentially, no. So there is one assumption.
Repeat the questions.
Okay. So the question was, am I approximating a point process via a Gaussian mixture? The answer is yes, star. Yes, asterisk, and I'll go over what the asterisk is. So one of the basic assumptions that we have to make is that jumps are relatively rare, in the sense that, so of course, a point process, you can have, well, infinitely many jumps between two observations. That would make things kind of crazy, and also the amount of Gaussian that we would need would be insane. So we kind of approximate the action of the jump operator by just, you have at most one jump for each interval, and then you're just looking at, whenever you have a jump, this is the distribution of the jumps that you have, and this is the object that we do convolutions with in some sense. So the jump density with Gaussians, exactly, yeah. And then, but this is kind of, in order for this thing to be more or less the same as the jump process, you need to assume that the jumps are rare, essentially. Does that kind of answer your question a little bit? So we're approximating the jump density specifically. That's a good point. Yeah. Yes, Master. Oh, how do I? So I think the question is, how do I? Well, we have these points, these particles, and how do we turn them into the Gaussians, basically, right? So this is kind of heuristic. What we do is we take one point, we take its k nearest neighbors for k relatively large. And within this cloud of points, we just take mean and covariance, and that's about it, right? So, but usually because we're using k and n, and we're mathematicians, we just assume that everything will work out in the end. I would say that this is relatively good, like weak model for how these Gaussians would work, at least.
As you're using a hacking method, so you're projecting to a small dimension subspace.
Yeah.
And you're projecting into the Gaussian space.
Yes.
And you said that some calculations can be very ugly when you use Gaussians, but can be easy using Fourier approximation.
Yes.
Why not using Fourier subspace too?
Okay. So the question was why we chose this basis specifically that has all of these complications as opposed to using the Fourier basis. And the problem with the Fourier basis is that it is grid-based, right? So if your spatial, say our SDE is of order 3, we need to split up. Now it becomes a PDE in 3 dimensions that we need to split up in, say, 100 pieces for each dimension. That's already 10 to the 6 Fourier harmonics that we need to take care of, right? If we have 4 or 5 or dimension 20, like we may end up having, we would need to have 100 to the 20th power Fourier harmonic terms, basically, right? Of course, there's all kinds of dimensional reduction that you could do. But the second cool thing about Gaussians is that, as I said, like the Kolmogorov, the Fokker-Planck generator, when it acts on Gaussians specifically, it has this super nice, very interpretable thing, which is, advection, deterministic transport just moves a Gaussian, diffusion just spreads it, jumps just split them. So, and then you can break down these actions very neatly. While in the Fourier domain, all of these would get kind of mixed up. Does that answer your question? Sorry, Pavel, yeah.
As a follow-up to this question, wouldn't it be more efficient to multiply Gaussian by some orthogonal polynomials, for which I guess you also could figure out more or less some nice rules for action of this operation?
Yes. So this was something that I thought of as well, not orthogonal polynomial, but using some kind of, I forgot the name now, when you multiply Gaussians by Fourier harmonics or something like this, right? Anyway. The point was just basically we didn't need it in the end. Things worked surprisingly well with just the Gaussians, moving the Gaussians around, that kind of stuff. Maybe what can become a problem, and this is something that I kind of push under the rug here, is that when you have lots of jumps, well, say you start with one Gaussian, and then you split up this Gaussian into three. Let's say your jumps can go to one of three places. Now you have three Gaussians. Next time you have a jump, you're going to have 9 Gaussians. And this kind of stuff keeps growing basically exponentially, right? So at some point we need to kind of cap the number of Gaussians that we have, and this becomes a mess very quickly. So fortunately for this, for the purposes here, because we're only trying to learn the dynamics and not simulate them very much, like this still works. But once these kinds of things, once the jumps become more complicated, I would probably do something like this. Not only using pure Gaussians, but Gaussians equipped with something else also. Sorry, just, yeah.
I have 2 questions. So the first one is, how, I understand that you guys created this method to solve a much harder problem.
No.
But say you're trying to use this method to solve something which doesn't, like, the noise doesn't exist, or like G0 or your jumps.
Yeah.
Like, would it be possible to use the same method? Because maybe you wouldn't be able to sample this Gaussian. I mean, I assume they would collapse into point.
Yes.
But,
so the question was basically, well, if you don't have noise, would this method still work, and how could we adapt it, basically, right, to the purely deterministic setting? And essentially what happens in the purely deterministic setting is that all of these Gaussians will just collapse to direct deltas, essentially, right? But because now everything has become deterministic, you're just going back. Sorry, I didn't go over this very much because the talk was long enough already. But in this limit case where you just have these direct deltas all around, you just need to look at where they're going. So, if I have one delta here and I know that 1 second afterwards it was there, because everything is deterministic, you can just say, oh, this is the dynamics, right? You don't need to be fancy about it. You can just interpolate using whatever tools you want, and things start becoming very much simpler. So to some degree, this is a generalization, right? And if you just collapse everything to direct deltas, we're back to the original deterministic case. Does that answer your question?
yeah, I do. And the other question I have, oh, sorry.
I just have a follow-up question.
Yeah.
If instead you consider just the first 2 terms, not the third term.
Not the jump term,
Would
right?
that make it much better?
For sure. So jumps made everything,
Yeah.
jumps were what, a substantial amount of hair loss that I've endured over the last 3 months was due to these jump operators. But the cool thing about only advection and diffusion is that you just need one Gaussian, right? And everything is just this one Gaussian, maybe spreads out, gets a little bit weird, but it's just one, nothing breaks up. So things get much, much simpler. And in fact, the dynamics get much nicer.
So in that way, you get more applications and more practicality considering what.
Yeah, for sure. Yeah. But again, hopefully what we would like this to be some kind of modular thing that if you need jumps, they're there. If you don't, everything should work also more or less in the same way.
Well, may I also a small follow-up to this same question?
Yeah.
Now, assume that we don't have any stochastics, but for some reason we still want to maintain Gaussian. So that means you basically exclude 2 terms of your 3 terms.
Yes.
Propagator, and still somehow it should work.
Yes.
I guess you can get some deterministic dynamics from Gaussian.
Yes.
As well.
So if you can, you will be basically just measuring the average behavior. If you just give up these two guys, these Gaussians would just be moving according to the deterministic trajectory, which also kind of works fine, I would say. But of course, at some point, this does break down. Like these projections onto this manifold are imperfect, so you can't really say that, obviously, for example, the Lorentz attractor, at some point your Gaussian would split into either one of the attractors, but these approximations are all short time, and in a short time they do work. Right? Or do we have any online questions, maybe something like that?
No, but a lot of output here.
Oh, okay, my friends are giving me kudos online. Thanks, friends, I really appreciate it.
Very good.
So I wanted to ask, so you mentioned that a big complication of this method is that like at each time that you choose to do, you have to sample these Gaussians and take a look at them.
Yeah.
Right. I was wondering if there's any way to, like, especially in physical systems where this particle is acted on by some random force, but also moves in such a way that it tries to minimize some work or some force.
Mm-hmm.
So in that way, if that was true, then maybe you wouldn't need to sample it because, or sorry, you might still want to sample it, but you like the way that the probability masses will move would also follow some minimization of
Yeah.
particles, and then maybe you wouldn't need to sample as many times.
Yeah.
So, I mean,
So basically what he's asking is, well, this issue with sampling and resampling all of these Gaussians all of the time. This is in fact a restriction due to the very, very broad assumptions that we're making, right? So essentially we're trying to model any continuous time Markov system, which is a very broad class of systems. But if you allow yourself, for example, if your system is a gradient system and your noise is uniform, there are no jumps, then you can do all kinds of other cool stuff. For example, we had a talk here last week by Vladi, that he basically, when you have very much stronger assumptions, your operators get much richer, and then you can do all kinds of crazy stuff with much less information. But our problem here is that we're trying to be super general, so that's a limitation in some sense. Yeah.
I have a question about the jump operators.
Yeah.
Well, I think that jumps occur like in real life, not so randomly. Like it happens after some random things add up, and then. So my question is, when you naturally learn, how can I say that the right time to have a jump, so that if you want to solve it like a pin, if you want to solve it with no initial data,
yeah.
It knows where, this is most likely to have a jump here.
Yeah.
Or it just places jumps randomly in a...
So right now, we're doing jump space, so these Poisson processes, as far as I can tell, and there are people much more informed that could answer this question, I think. These jumps, they are just essentially random. And the way our hypothesis that this process should be Markov and infinitely divisible, as they call it, kind of force them to be random. What you could do, so I agree with you, and this is one of the big limitations also, is that, obviously jumps in nature, they don't just happen completely randomly. There's usually some kind of hidden factor that makes them happen more or less often, right? So you could model this as some kind of latent hidden state or something like this. But in that case, next paper.
Usually what you have is that the density function of the process can evolve with time.
Yeah.
So it can depend on the trajectory of the process.
Yeah. So we did try to kind of model the for example, the dynamics of the intensity function somehow, right? So how often the jumps would take. But we essentially just didn't have enough time to make it work well, because it can be relatively simple, if jumps start happening more as things get further ahead, cool. But then you also start needing like a huge amount of samples to be able to draw this kind of information in any kind of reliable way. Any more questions? Should I? By the way, if anyone needs to go, I will forgive you. It's fine. Tell me. Yeah. Yes.
Okay. So I like the idea of going back from your lead rotor splitting and showing that it's actually transforms into backwards into Euler-Mariyama. But
This one?
yeah, but the one, assume now that you're using strength splitting, which obviously is a lot better because it's second order. Assume that you try to go backwards. Which numerical scheme you recover from your stochastic differential equation?
Okay, so the question was basically, so from a operator perspective, this lead rotor splitting becomes this Euler-Mariyama stochastic integration scheme. What would be the stochastic integration scheme that is implied by this strength scheme? I don't know the exact answer to that, but I can tell you that this is very, very similar to a Hewn, don't know how to, so there are all of these stochastic predictor corrector schemes that are almost like this, right? Because so strength splitting, what we do is we do these kinds of trapezoidal differences on the data somehow, and this Hewn scheme kind of approximates this kind of stuff. So in my view, when implementing these guys, I use the Hoyne, possibly, scheme, and it seems to work.
Hoyne scheme is equivalent to some Runge-Kutta second order. That's the point. So I guess when going back from strength splitting backwards to this numerical integrator, you basically recover some Runge-Kutta 2 for...
Yeah, some stochastic Runge-Kutta 2, yeah.
And I'm not sure how this is relevant or not, but the whole theory of this stochastic numerical integrators for differential equations, in the case of manifolds, maybe it's worth looking into that thing when you're restricted to some manifold. I'm not sure what can be the application area, but it feels like there should be something.
Yeah. So the point was that there are better integrators also that also work on manifolds. It can be more accurate. The problem is that here our error here is much more constrained by this constant projection and reprojection onto the Gaussian manifold than anything else. And then this projection, there's also in the paper, it's second order also. So it doesn't really make much sense to go beyond strength because we're going to get second order errors in any case.
No. I'm not saying you should go somewhere upwards, but you can take a look at what happens when you're restricted to manifold. Stochastic manifold integration.
Yeah. Stochastic manifold integration might be a good idea for sure.
I have just one
Wrap-up question.
Sure.
So, for training, you need a path, right?
Yes.
Do you have an idea how to use this framework for distillation? Like you have like diffusion models, like a very large diffusion model.
Okay.
And then you define your model and you are going to distill just a piece of that.
Yeah. So moderately bright minds think alike. I was thinking about this morning, and in fact, that was one of the big large-scale applications that I was thinking about. Because if you can observe, well, each one of the steps of your diffusion model, which we can, right? You're just integrating some SD with some very complicated vector field. By just observing how this noising, denoising process goes and feeding this into the architecture, again, the problem is that these diffusion models tend to work in very high dimensions. But if this wasn't a problem, or if this was some very small scale diffusion model, we could just basically do distillation using this exact framework, and things hopefully should work. Again, assuming that it's low dimension, Gaussian mixtures work, all of that stuff.
And maybe learning some lower dimensional structure from the
Yeah, these guys probably exist in some kind of latent space anyway, right? And then in these latent spaces, it might be low dimensional enough so that we can do distillation.
Assuming right now you are using a very simple network, right? Parameterize that.
Yeah, it's just some MLP 1-2 hidden layer. I don't even remember. Right. Okay, fellas. So thank you so much for your time. Folks online, also, thank you very, very much. And yeah, any